All right, so homework 18 starts off with the area of a sector of a circle. So when we had that circle, and I was finding the arc length, now what we're going to do is find the area in there. And so the formula for the area is 1/2 the radius squared times the measure there of that central angle, and again the central angle needs to be in radians. So it says a circle has a radius of 2.5 inches. The sector of the circle has a central angle of 2 pi over 3 radians. Find the area of the sector. Do not round any intermediate computations. Round your answer to the nearest tenth. So my area is equal to 1/2 times the radius squared, so 2.5 squared, times the central angle in radians, which it is, so 2 pi over 3. So in this case, again, I would want to use the pi button on my calculator so I don't have to worry about rounding issues. I'm going to use fraction button, 1 fraction half, 1/2, times 2.5 squared, times 2 shift the EXP button, and then fraction 3, 2 pi over 3. You could use the division, but I'm just going to use the fraction. And so when I hit equals here, I get 6.5449. I'm rounding to the nearest tenth, so I didn't really need to take it that many places, so 6.5. Since I'm finding area, I'm in inches, so area inches squared. So 6.5 inches squared would be my answer. So a circle has a radius of 8.5 feet. A sector of the circle has a central angle of 4.3 radians. Find the area of the sector. Again, just using my formula, area equals 1/2 times the radius, so 8.5 squared, times the measure of the central angle. And this one, they have the decimal equivalent, so I don't even have to worry about the pi. I'm just going to punch that into my calculator. Now you could use 0.5, obviously, for 1/2. Either way, 1/2 times 8.5 squared times 4.3 then. I get 155.33. Rounding to the nearest tenth then, 155.3. I'm in feet, so my area would be feet squared. So 155.3 feet squared. And I got to move the board up for number 3 here. So on number 3, it says the area of a sector of a circle with a central angle of 5 radians is 11 feet squared. Find the radius of the circle. So area is equal to 1/2 r squared times theta. We know the area is 11. We are finding the radius. The central angle is 5. So 1/2 times 5 would be 2.5. So we're going to have to take 11 and divide it by 2.5 to find r squared. 11 divided by 2.5 gives me 4.4 to equal r squared. And since we just want r and not r squared, we then have to take the square root. So square root of 4.4 gives me 2.09. I'm rounding to the nearest tenth, so 2.1. This was feet squared for the area, which tells me this is feet since I'm just doing the radius, so 2.1 feet. All right, 4, 5, and 6 have to do with angular and linear speed. For angular speed, it's how fast your wheel is spinning around. Linear speed, how far a distance does that cover? So it says a Ferris wheel at a carnival has a radius of 36 feet. Suppose it turns at a rate of 70 revolutions per hour. Do not round any intermediate computations. Round your answer to the nearest whole number. we want to find the angular speed in radians per hour. Well, we know the speed in revolutions per hour. So we want to convert our revolutions into radians. We know that 1 revolution is 2 pi radians. So we want to do our conversions. Since I want to cancel out the revolutions, I want 1 revolution on the bottom. That means the 2 pi radians would go up on the top. And then I got to grab my calculator. Again, for pi, I would use the pi button on the calculator so that you don't get any rounding issues. But basically there, we're just going to take 70 times 2 pi. So 70 times 2 pi gives me 439.8. We're rounding them off to the nearest whole number, so we're going to round that off to 440 radians per hour. The next part there, we want to find the linear speed. The linear speed is how much distance it would cover if it was rolling along the ground. And so for the linear speed, we're going to take the radius times the angular speed. Told us right up here that the radius of our carnival wheel is 36. So we're going to take the 36 times, and we don't want to use this rounded off number. So we want to go back to what we did for our calculation in order to get that number, 70 times 2 pi. That's going to give us our answer in radians per hour. We want it in per minute instead of per hour, so that since this is in per hour, we want to change, or we want to take that 1 hour is 60 minutes. And so I'm going to take 36 times 70 times 2 pi. I'm going to hit equals there, and then I'm going to divide it by 60. And I'm coming up with 263.89. So I'm going to round that off to 264. Since this was in feet already, we didn't have to change that. That's in feet. And now it's per minute, since we changed our hours to minute. So 264 feet per minute would be my answer. So we took our radius times our angular speed, and then we had to convert our units. Since this was in per hour, we needed to change it into minutes. So number 5 says, suppose that Uranus rotates on its axis once every 17.2 hours. The equator lies on a circle with a radius of 15,881 miles. Do not round any intermediate computations. Round your answer to the nearest whole number. So we've got 1 revolution in every 17.2 hours. We want to change it into radians per day. So if I first of all deal with my hours, we know that there are 24 hours in a day. So that will give me revolutions per day. We want to change our revolutions into radians, and so we know that 1 revolution is 2 pi radians. So their revolutions cancel out, our hours cancel out, and we get radians per day for our units. So we end up taking 24 times 2 pi. I'm going to go ahead and hit equals for the top number, and then I'm going to divide it by the 17.2, which is on the bottom. And so I end up getting 8.76. I'm rounding to the nearest whole number, so I'm going to say 9 radians per day. So 9 radians per day. Then we want to find the linear speed. We know that the linear speed, we're going to take the radius. The radius is 15,881 miles times our angular speed. But again, we want to be careful that we don't use the rounded off. So I'm going to use the 24 times the 2 pi divided by the 17.2. And that's radians per day. We want miles per day, so we've got the right units. So I'm just going to go ahead and punch that in. So 15,881 times 24 times my 2 pi. I'm going to hit equals, and then I'm going to divide that by my 17.2. And I'm coming up with 139,232.46. So 139,232 miles per day would be my linear speed. So on number 6, it says that a cyclist is riding a bicycle whose wheels have a diameter of 30 inches. Suppose he is traveling at 22 miles per hour. We know that 1 mile is 5,280 feet. Do not round any intermediate computations and round your answer to the nearest whole number. We want to find the angular speed of the wheel, in radians per minute. Got a little typo on there. So we know that we are going 22 miles in 1 hour. I want to go per minute. So 1 hour is 60 minutes. I also need this, whoops. So that I can change it into radians, but since my units up here is in inches, I have to change my miles into inches. So I am going to say that I have, let's see, 1 mile is 5,280 feet, but then I have to change my feet to inches. 1 foot is 12 inches. So I'm going to take 22 times 5,280 times 12. I'm going to go ahead and hit equals. I'm going to divide that by 60. So we have 23,232. This is in inches per minute. We know that the diameter of the wheel is 30 inches, so if I divide that by 2, the radius is 15 inches, so we would have 15 inches times that angular speed. So what we end up having to do to change it to radians per minute is that we end up having to divide by that diameter of 15. So I'm going to take my 23,232, I'm going to divide it by the 15-inch diameter, and I get 1,548.8, so I have to round that off to 1,549. Now it's in radians per minute. Now we want to change that into how many revolutions per minute. And so I'm just going to use this one since it wasn't rounded off too far. 23, 23, 2. 23,232 divided by 15 is in radians per minute. I want to make it revolutions per minute, so I'm going to change radians. 2 pi radians is 1 revolution. So I'm going to use my conversion for radians, making sure the radians are on the bottom so they cancel out. So I'm going to take my 23,232. I have to divide that by, and since there's more than one thing on the bottom, I'm going to use parentheses. So parentheses, 15 times 2 pi, close my parenthesis, and I get 246.49. So rounding that off, 246, and that would be in revolutions per minute. And you do need to be careful here, since you've got more than one thing. You can either put parentheses around the bottom or do this divided by 15 and then divide that by 2 pi. That would also work. So it might take some practice trying to figure out how your calculator works, but I did the 23,232 divided by, and in parentheses, put my 15 times my 2 pi. All right, the next ones are our special angles that we have. When we were talking about the radian measures, we were either talking about 30, 60, 90 degree angles, or 45, 45, 90 degree angles. So when we looked at our unit circle and we were plotting them in radians, one of these triangles is going to become our reference triangle on our circle. So for 30, 60, 90, the side opposite the 30 is going to have a length of 1. The hypotenuse will have a length of 2. Using the Pythagorean theorem, you could figure out that the side opposite the 60 is going to be square root of 3. So those are always the standard that we use for a 30, 60, 90. Opposite the 30 is 1, opposite the hypotenuse is 2, and opposite the 60 is square root of 3. When we have a 45, 45, 90 triangle, the sides opposite the 45s will each be 1. That makes the length of the hypotenuse the square root of 2. A squared plus b squared equals c squared. So the ones opposite the 45s will always give up 1 unit, and that makes the hypotenuse square root of 2. So when we are looking for the points, we're thinking about where is that angle in our circle. 5 pi over 3 is over here, with this being a 60 degree angle, so that one's a 30 degree angle. So the side opposite the 30 would be 1. The side opposite the hypotenuse would be 2. The side opposite the 60 is normally the square root of 3, but notice it's going down, so it's negative square root of 3. So when I'm giving the coordinates, what I'm doing is I'm giving the x-coordinate is the cosine, the y-coordinate is the sine, and I'm putting it in as an ordered pair. Cosine is adjacent over hypotenuse, and the sine is the opposite over the hypotenuse. So when I look at this one, the adjacent is 1, the hypotenuse is 2, so my cosine is going to be 1/2. My opposite is going to be negative square root of 3. My hypotenuse is 2, so negative square root of 3 over 2. And so my terminal point on my unit circle then would be at 1/2 and negative 3 square root of 2. If I'm doing 3 pi over 4, then I'm talking about a 45, 45, 90 triangle. 1 pi over 4, 2 pi over 4, 3 pi over 4. So there's my reference triangle. My reference triangle always goes down to the x-axis. So we've got a 45, 45, 90. So 1, 1, and the square root of 2. However, this is going backwards, so that one's going to be negative 1. So cosine, my adjacent over my hypotenuse. Well, if I have to do my adjacent over my hypotenuse, I'm going to get 1 over the square root of 2, and of course I'd want to rationalize that denominator by multiplying by the square root of 2 over the square root of 2. So I get negative square root of 2 over the square root of 4, which is just a plain 2. My sine, going to be similar to that, but it's going to be a positive 1 over the square root of 2. And if I have 1 over the square root of 2, again, I have to rationalize that, so I get a positive square root of 2 over 2. So number 9, we want to find 4 pi over 3. We're going to change it into pi over 6. So I'm going to do 8 pi over 6. So 1 pi over 6, 2 pi over 6, 3 pi over 6, 4 pi over 6, 5 pi over 6, 6 pi over 6, 7 pi over 6, 8 pi over 6. So my reference triangle is going to be down here in quadrant 3. I'm going to redraw it. With this being the 60-degree angle, so that one's 30. So I would have 1, 2, and the square root of 3, but this is going backwards, so it's negative. This is going down, so it's negative. And so my cosine would be the adjacent over the hypotenuse, negative 1 over 2. My sine would be the opposite over the hypotenuse, so negative square root of 3 over 2. Now, I did those all by drawing my reference triangles and knowing all those things about sine and cosine. On ALEX, for right now, they're going to have the information kind of drawn out for you on a table. So if I go over to Linda's note sheets, over here, on the ALEX program, they're going to have these nice little tables for you. So if you look at the first one was 5 pi over 3. So I want to use the ones that are multiples of pi over 6. 5 pi over 3 you can see is way over here. You can see the answer, 1/2 and negative 3 pi over 2. The second one that we did was 3 pi over 4. 3 pi over 4 was right here. You can see that they got negative square root of 2 over 2 and positive square root of 2 over 2. And then the last one was 4 pi over 3. So 4 pi over 3 you can see is right down here, negative 1/2 and negative square root of 3 over 2. So you'll be able to either look at Linda's note sheets, or if you print and explain from ALEX, they might have these separately, one for the multiples of pi over 4 and the other one's for the pi over 6, the 30, 60, 90s. So you might want to just print out my note sheets, but try drawing your reference triangles and then double check by looking at their chart to see if you're getting the same answers, so that you get used to the reference triangles, and that the 45, 45, 90 is 1, 1 square root of 2, and that the 30, 60, 90 is 1, 2 is the hypotenuse and the square root of 3, and then doing the sine and the cosine for the x value and the sine for your y value. And so for right now on ALEX, they're just going to give you the chart so that you can kind of look at it, but you want to get used to your reference triangles. So the next ones now, they're going to give us the coordinates and tell us which quadrant we're in, and they want us to find the x or the y value. So again, on my coordinates, the x is the cosine, so the adjacent over the hypotenuse. The y is the sine, so opposite over hypotenuse, kind of like on those previous ones we had. So what we want to do is sketch this. We have a point in quadrant 2, so it goes this way. And we know what the sine is, so we know the opposite side and the hypotenuse. So the opposite side, we're always going from this angle here. The opposite side is 7, the hypotenuse is 25. We need to find that other side by using our Pythagorean theorem. We know that a squared plus b squared equals c squared. And so we know that 7 squared plus b squared equals 25 squared. b squared is then going to equal 25 squared minus 7 squared. So 25 squared minus 7 squared gives me 576. So b is going to equal the square root of 576. And so b equals 24. So since this was b squared, I had to do the square root of my value there to get just plain b. Now this is going backwards on my x-axis, so instead of being 24, it's actually going to be a negative 24. And so x then is going to be equal to the adjacent over the hypotenuse, that negative 24 over 25 then. So on number 11, now we have the point 725 in y. It's a coordinate in quadrant 4. So down here, we know the first value, which is the cosine, the adjacent over the hypotenuse. So the adjacent is 7, the hypotenuse is 25, and again, we'd have to find that missing side. Well, again, 7 squared plus b squared equals 25 squared, which we did on the previous one. So b squared equals 25 squared minus 7 squared. B squared is going to equal 576, so the square root of 576 is going to give us 24 again. And again, this one is going down, so that's actually going to be negative 24. So our value for y is going to be the opposite over the hypotenuse, the opposite side, negative 24 over 25 then. And number 12, same kind of thing, at least they gave us different numbers. This time we have a point that is on quadrant 2. So in quadrant 2 we have our first value. Our first value is our cosine, so our adjacent side is negative 12. Our hypotenuse is 13. Your hypotenuse is always positive. So if you have the sine or the cosine, the negative is going to have to go with the top because the hypotenuse is always positive. And then again, we have to find that missing side. So negative 12 squared plus b squared equals 13 squared. B squared is going to equal 13 squared minus my negative 12 squared. And you know when we square that negative, it's going to become a positive. 13 squared minus my negative 12 squared, make sure you use the parentheses, is 25. B squared equals 25, so the square root of 25 is 5. This side is going up, so it should be a positive 5. And then we are finding the y value. The y value is the opposite over the hypotenuse, so the opposite over the hypotenuse, 5 over 13. So basically we're going to use the Pythagorean theorem to find our missing side so that we can figure out what our other point should be in our reference triangles. And again, keep in mind when you draw that reference triangle, it always goes down or up to the x-axis. So if my angle was in quadrant 4 like this one, I draw it up. So in quadrant 3 I go up. Quadrant 1 and quadrant 2 I go down to draw my reference triangle. Alright, the next one now they're getting into the sine, cosine, and tangent ratio. So now getting more into some of the things that we've already touched on, and that's why they give you a chart on some of those. First of all, if I have my triangle, my right triangle, and this is the angle that I'm working for. This is my opposite side. This one's going to be my adjacent side. And this is going to be my hypotenuse. So the opposite, you always can just go straight across. That's going to be your opposite side. So I'm going to do sine, cosine, and tangent. The sine is the opposite over the hypotenuse. Cosine, whoops, I'm trying to write cosine there. cosine is going to be your adjacent over hypotenuse. And your tangent is your opposite over your adjacent. So those are your three basic trig functions. We will have some more that are the inverses of those, but just to start out with, they're just going to have you name what the sine, the cosine is, and tangent is. They've already got the triangle labeled for you, so you don't even have to find anything. So my sine, I am doing of angle B, so my opposite would be 12 over my hypotenuse, 13. My cosine, my adjacent, the one right next to it, would be 5 over my hypotenuse, 13. And my tangent would be the opposite over the adjacent, so 12 over 5. So again, we have our right triangle. They've got it all turned around, but this is the angle that they're going to look for. And they switched it around. They're going to have you do the tangent first, the cosine, and then the sine. So my tangent is my opposite side over my adjacent side, so 5 over 12. My cosine is going to be my adjacent side over my hypotenuse, so 12 over 13. My sine, opposite over hypotenuse, 5 over 13. So the hypotenuse is always opposite the right angle. The opposite is opposite the angle you're next to, and the adjacent should be that other side that's right next to that angle when you're looking. Move that so we can see number 15. So number 15, this one is going to have us do the sine first, then the tangent, then the cosine of angle B. So angle B, my opposite side, 15 over my hypotenuse, 17. My tangent, opposite over the adjacent, so 15 over 8. My cosine, adjacent over hypotenuse, 8 over 17. So some things do this. They say SOHCAHTOA, sock, opposite hypotenuse, ka, toa, SOHCAHTOA. I have a sock on my toa. Sock, opposite over hypotenuse, cosine, adjacent over hypotenuse, tangent. No, that's the wrong thing. Tangent, opposite over adjacent, toa. So, I make my fractions. Sine, opposite hypotenuse, cosine, adjacent hypotenuse, and tangent, opposite over adjacent. Better put the right thing there, SOHCAHTOA. (16, 17, 18), basically doing the exact same thing we did on the previous problems, but this time now they're going to use variables instead of numbers. So we want to do the cosine, the sine, and the tangent. We said that sine was opposite over hypotenuse, cosine is adjacent over hypotenuse, and tangent is opposite over adjacent. So my cosine of angle X, here's angle X, so this would be my opposite, so my adjacent would be A over C. My sine is the opposite over the hypotenuse, so B over C, and then my tangent, opposite over adjacent, so B over A. (17), same kind of thing. I'm going to do the tangent, then the cosine, and then the sine. I always like to point out my opposite one first because that's the one I got to use for my reference. So my tangent, opposite over adjacent, E over F. My cosine, adjacent over hypotenuse, F over D. My sine, opposite over hypotenuse. E over D then. So on number 18, we're going to do the cosine, then the sine, and then the tangent. And so my opposite sides here, my cosine is the adjacent over the hypotenuse. So A over C would be my adjacent over my hypotenuse. My sine, opposite over hypotenuse, B over C. My tangent, opposite over adjacent, B over A. So again, sine is opposite over hypotenuse, cosine adjacent over hypotenuse, tangent opposite over adjacent. Sa, ka, toa. Crazy, I know. (19, 20, and 21 goes back to finding the value of sine, cosine, maybe even tangent in the angles that we have. So again, we have to kind of know where they're at, and we have to know our reference triangles. In this case, since it's a pi over 6, we know it's going to be a 30, 60, 90. So this would be 1, 2, square root of 3, but we have to figure out where 11 pi over 6 is. So 1 pi over 6, 2 pi over 6, 3 pi over 6 is right there. 4 pi over 6, 5 pi over 6, 6 pi over 6 is the same thing as pi, 7, 8, 9, 10, 11. So 11 pi over 6 means that this is a 30, 60, 90 reference triangle. So we know that this side is 1, the hypotenuse is 2, this side is the square root of 3, except for this one goes down, so instead of being a positive 1, it's going to be a negative 1. Let's make my negative in there. We want to do the cosine. Cosine is the adjacent over the hypotenuse. So my adjacent one is going to be the square root of 3. The hypotenuse is going to be 2. So square root of 3 over 2 is going to be what my cosine is equal to. Here we're doing 5 pi over 4. Since it's over 4, we know that it's a 45, 45, 90. You want to draw it that way? So if it's a 45, 45, 90, we've got 1, 1 in the square root of 2. Figuring out where that's at. 1 pi over 4, 2 pi over 4, 3 pi over 4, 4 pi over 4, 5 pi over 4 ends up being over here in quadrant 3. We know it's a 45, 45, 90, so 1, 1 and the square root of 2. However, this is going back, so it's negative. This is going down, so it's negative. And so if we're going to do the sine is the opposite over the hypotenuse. The opposite side is going to be negative 1 over the square root of 2 then. We have to rationalize the denominator. So we multiply by the square root of 2 over the square root of 2. We get negative square root of 2 over the square root of 4, which of course simplifies, so we get negative square root of 2 over 2. Number 21, they gave it to us in degrees, but it's a negative degrees, so negative 315 degrees means you're going backwards. If I take 360 and subtract 315, that gives me a 45 degree angle. So again, we've got that 45, 45, 90. So 1, 1 and the square root of 2, that's positive, that's positive. So if I'm going to do the cosine, I'm going to do the adjacent over the hypotenuse. My adjacent side is 1, so I get 1 over the square root of 2. And again, when I rationalize that one, which you'll do a lot, we end up with the square root of 2 over the square root of 4, which is the square root of 2 over 2. Now again, on these ones, if you look at the Alex note sheets or my note sheets, you're going to have those tables. like we did on those previous ones where we had to pick out the coordinates of our angle. Remember that the first one is the cosine and the second one is the sine when you're looking, if you're looking at those circles where you have those for reference. Just keep in mind that if I were doing 5 pi over 6, the first one should be my cosine answer, the second one is my sine answer. So here's your 60-degree angles, or here's your 30-degree angles, here's your 60-degree angles, and then over on my next page would be the 45. And then actually we got the 90-degree angles on there also. So if you're looking at those to kind of double check to make sure it looks right, you can print those out on the Alex notes or on my note sheets to have those reference circles already drawn. Keep in mind the first one's a cosine, the second one's a sine.